In today's class, you are going to learn about application of dimensional analysis. How to use dimensional analysis to derive the unit of a physical quantity, and also to determine the correct form of an equation. Let's say an equation is given to you, you've forgotten the form to which an equation is being written. You can actually use dimensional analysis to check if you are correct. And also, you can use dimensional analysis to derive or detect how different physical quantity relates to each other. So let's say 3 to 4 physical quantity is being given to you, and you're asked how do these physical quantity relates to each other. You can actually use dimensional analysis to detect that, and that's actually one of the applications of dimensional analysis. So quickly, let's check the first one. So let's say velocity. If you know the dimension of velocity, you can easily get the unit of velocity. So for velocity, say velocity is the displacement all over time, and this is equal to, using the idea of dimensional analysis, displacement is length and time is represented with t. So we have t into the power of minus 1. If you are finding it difficult to understand what I did here, do well to check in the video description. I have a class that covers the basis of dimensional analysis. It will be very hard for you to relate to what I'm doing now if you haven't gone through that video. So do well to check through the video on dimensional analysis before coming to check the applications. So now from this is actually the dimension of velocity. Now looking at this, assuming I don't know the unit of velocity, from the dimension I know that this is length, and length is measured in meter. So this is meter multiplied by what we have here is time, and for length the unit is meter, for time the unit is second. So what we have here is second. So this is now the unit for velocity. So with the help of the dimension of velocity, we've derived the unit for velocity. Let's see for acceleration. We have that acceleration is velocity all over time, and this is equal to L multiplied by t to the power of minus 1 all over t. So this is equal to L multiplied by t to the power of minus 2. Now this is the dimension for acceleration. Now, being that you know the dimension of acceleration, let's see how we can derive the unit from this. So this is length. We know that length is measured in meter. So this is meter, and multiplied by, we know that t is time, and time is measured in second, which is the unit for time. So we have that this is meter multiplied by second to the power of minus 2. So this is now meter per second. So for acceleration, given the dimension, we use it to get the unit of acceleration, which is meter per second. Same thing to velocity, meter per second square. For velocity, meter per second. So for every physical quantity that is given to you, if you know how to get the dimension, from the dimension you can actually get the unit of that physical quantity. Let's check the application, the second application, which is to determine the correct form of an equation. Now, observe the two equations of motion on the board. Let's say you are in an example and you just forgot the direct way of writing this equation. Maybe you forgot is it t squared or just t. You can actually use dimensional analysis to check if what you have written is correct or not. Now, for this to be true, there is a principle that you need to be familiar with, which is the principle of dimensional homogeneity. This principle states that for an equation to be correct, the right hand side, the dimension of the right hand side must be equal or must be the same as the dimension of the left hand side of the equation, irrespective of the numerical value or the coefficient attached to one part of the equation. So what that simply means is that if you have an equation A is equal to B plus C, the principle says that the dimension of A must be equal to the dimension of this. If you derive the dimension of this and the dimension of this and you add them, the dimension that you are going to have will be equal to the dimension of this for this equation to be correct. So let's say the dimension of this is given as this. The principle says that the dimension of this must be equal to this. So when you add up the dimension of this and this, it must be equal to, it must be m multiplied by t to the power of 2. And the other part of principle also says that irrespective of the coefficient attached to one side of the equation. So we can have 2 here. Let's say when you add up this and this, let's say this is m multiplied by t to the power of 2 plus m multiplied to the power of 2 multiplied by t to the power of 2. When you add them, you have 2. So provided this and this is equal, irrespective of this value, this equation is said to be correct. So with this idea, we can now put down the dimension of this and resolve the dimension of this expression. If what we have here is the same thing as what we have here, then the form to which you have written the formula is said to be correct. So let's see about that. So let's try to, we know that this equation is correct, but let's use dimensional analysis to confirm it. So we have that the dimension of this is L, because this is distance. So we have that distance is equal to initial velocity multiplied by time plus half multiplied by A, which is acceleration, multiplied by time all squared. So the dimension of S, which is distance, is L. This is equal to the dimension of velocity is L all over T. The dimension of time is T. We have addition sign. What we have here is 1 over 2. So this is acceleration. The dimension of acceleration is L all over T to the power of 2. This is T squared. This is time and is represented with T for each dimension. T all squared. Now, what we have here is L equals to, so L equals to this. So this can cancel out. We have that this will cancel this. So what we have here is L plus this This is equal to what we have there is L is velocity. What we have here is velocity. Velocity all over L all over T. What we have here for acceleration, we have it as L all over T all square multiplied by T. Now, simplifying this, we have that L multiplied by T to the power of -1 is equal to what we have here is L multiplied by T to the power of -1 plus this will cancel this. We have one of the T left. So we have L multiplied by T to the power of 2. So this is equal to M multiplied by T to the power of -1 is equal to this, this is T to the power of -1 because this cancels out remaining T. We take T this way, it becomes T to the power of -1. So you can see that this and this are the same, so we can add them up so that we have 2L multiplied by T to the power of -1. Yes, so you can see that the equation is correct. So this part of the equation is the same thing as this part of the equation, confirming that the equation is correct irrespective of this coefficient. So this is how you can actually check. To any equation you've written, if you check the dimension of one part of the equation and simplify the dimension of the other part of it, which is the right and left hand part of the equation, if they are not the same, it means you've written the wrong form of that equation. So let's see how we can use dimensional analysis to find the direct relationship or the correct relationship between two or more